With the curve? Without the curve?
Yeah. Okay, so today we're going to continue on with Chapter 5, a little bit of pre-calc review here. In particular, we're going to talk about inverse functions. Not one of my favorite things in the world, but we got to get it done. So, from your vast stores of mathematical knowledge, what can you tell me about,
Excuse me, what can you tell me about?
inverse functions? What do you know about them? What's up, banana boy? You doing? Living the dream. Got anything for me about inverses? No? Nothing? Okay, anybody else? Amanda? You're pretty smart.
I don't know. It sounded familiar when you first said it, then it left my head.
When they get a mini stroke, you just
Yeah.
you forgot your middle name and what inverse functions are.
Yeah.
Okay, great. Anybody else have a mini stroke or no?
I think there was an
You know nothing about inverse functions. I'm sorry?
Switch X, Y, and solve for Y.
Well, that's something, right?
What'd you say?
Switch x and y and solve for y. What does that do for us?
Inverse the function.
Pretty much, yeah. Helps us find the inverse function. So if I take a simple function like y equals 2x plus 3, I turn the x into a y, turn the y into an x, solve for y, the thing I get is the inverse function. Okay, good. That's how to find it. We're not going to do a lot of that because that's tedious and boring. We're going to do more fun stuff, more funner stuff. Okay, we got nothing? All right, well, anyways, we're going to verify that a function is one-to-one, therefore looking at whether or not it has an inverse function. All functions have inverses, but not all inverses are functions. Does that statement make sense? Want me to say it once more?
Yeah.
All functions have inverses, but not all inverses are functions. Okay? Example would be if you take a parabola, for instance. You take the inverse of a parabola, it's actually a parabola on its side, no longer a function. So it still has an inverse, but that inverse isn't a function. So we're going to be concerned about inverse functions. We want that inverse to be a function. Then the fun stuff happens when we're going to take the derivative of an inverse function. There's a formula for that, or there's a logical process. I like the logical process better. I'll show you both. And then, of course, with the start of second semester, just simply be nice to people. Okay.
What's that?
Did he just tell you that off or something? What's wrong with you?
Because he committed, that's why he's like thinks
You
it's
think
a
you said second
Still soft.
statement be determine whether the inverse has a function?
No. Determine whether a function has an inverse function. It has an inverse. We're wondering if that inverse is a function.
Yeah, second line.
You just wanted to break me down, didn't you?
I was trying to be nice and fix it, but it was already.
By calling me out in front of everybody. Let me point out the last step here. Right, Alex?
Yeah.
Yeah, okay, good.
I can do it safely.
What if we're not nice to people?
This is America. You can do whatever you want.
Get used to hearing that.
Okay, so we got some inverse functions. Notice the notation here. That's not the reciprocal of f, it's the inverse function. And number one is important. The domain of the function equals the range of the inverse. The domain of the inverse equals the range of the function. So they switch domain and range. That's why you switch the x's and the y's. Domain is x, range is y's. You switch the two, you're done. The other thing that's helpful is to remember that an inverse undoes what you are doing in the original function. So for instance, if my function is simply a squared function, how do you undo a squared function? Square root. If your function is adding, you undo adding with subtracting, you undo multiplication with division. It undoes itself. Which helps you with this little guy here down at the bottom, that if you take a function and its inverse, you make a composite of those two, you will always end up with x. And that's how we're going to test to see if two functions are actually inverses of each other. We're not going to do so much as, here's a function, calculate its inverse. We're going to do the work that says, here's a function and this other function, are those things inverses? And it's a pretty simple check. Plug one into the other, see if you get x. Okay, which is what this says. Plug the inverse into the function, you should get x. Plug the function into the inverse, you should get x. And by the way, you got to check both. Excuse me. Okay, good?
No.
No. All right, here's two functions. There's a pretty good chance that these are inverses of each other because A, I'm using it as an example, and B, this is a cubic function, this is a cubic root function, so hopefully it works out. And notice I didn't ask you to find the function, I just want you to verify that they are in fact inverses of each other. So let's do some math. Okay. Nope. Come on. There we go. Okay, so I'm going to find f of f inverse of x. Which means I'm going to take the inverse, which, maybe I don't want to write that. I'm actually going to find f of g of x, because I don't know that it's an inverse yet, so my notation's a little sloppy. I'm going to take g of x, put it into x wherever I see an x. And so this becomes 2 times the quantity, the cubic root of x plus 1 over 2 cubed minus 1. And if they're inverses, I should get x. Well, the cubic root of something cubed is itself. So this would cancel with this. I get an x plus 1 over 2. That would cancel with the 2. I got a plus 1 and a minus 1. And sure enough, that gives me x. That's half of it. I have to check both. Now I need to take f of x and put it into g of x. So I want g of f of x. Take this function, which is the cubic root of wherever there's an x, I put in a 2x cubed minus 1 plus 1 over 2. And this one simplifies even faster. The 1's cancel, the 2's cancel, the cubic root of something cubed is x. Check didn't work out there. There we go. They are inverses of each other. Okay. Easy, yes? Good. And they won't be much more complicated than that. This is important, however. If you graph a function and its inverse, geometrically speaking, they are reflections of each other over the line y equals x. And when we get to the derivative of an inverse function later, you could use the formula, but I found the formula is rather difficult. If you remember this fact and one other simple fact, you'll be good to go. The other simple fact is this. If I take a point on this original function, let's take this point here, and we'll call it a comma b. And I take that point a comma b and I reflect it over the line y equals x, it's going to end up over here on that inverse function. What's the coordinate of that second point? Right.
Negative a comma negative b.
Nope.
Or negative a comma b.
Nope.
Negative b comma a.
Nope. B comma a. Okay, the variables just switch. Because remember, we switch the x's and the y's to find the inverse. So, again, two important things to remember. The inverse is the reflection over the line y equals x, and the point AB goes to the point BA. The coordinates change places. Okay? Gesundheit.
Thanks.
Did that already. Horizontal line test. You've done the vertical line. Did you do horizontal line test last year?
I think I've heard
Yeah,
about
we
it.
can get
Yeah.
Yeah.
Okay, so let's back up. What does the vertical line test do?
Which is the vertical line of the function. If it touches 2 points from the same function, then it's not a function.
Good. Say that again loud and proud, Alan.
You draw a vertical line through what you think could be a function. If it hits it twice, or if it intersects a function twice, then it's not an actual function.
Any vertical line, right?
Yes.
Yeah, any vertical line through a function, if it hits it more than once, 2 or more, then it's not a function. So what does the horizontal line test do? Well, now you get into some geometry. If I take a function, I reflect it over the line y equals x, I get the inverse function. And if I reflect a vertical line, the reflection of a vertical line becomes a horizontal line. So what does the horizontal line test do? The horizontal line test tests whether or not an inverse is a function. Okay, so if I draw a horizontal line anywhere through a function and it hits in more than one spot, then its inverse is not a function. And the easiest way to remember that is to think of a parabola. Is that parabola a function?
Yes.
Yeah, because it passes the vertical line test. Is its inverse a function? And hopefully you see by now the answer is no, because if I do that, draw a horizontal line there, I hit in more than one spot, and therefore its inverse will not be a function.
Could you just do the vertical line test with the inverses?
Very good. Yes. Did you hear that?
Yes, I did.
Yeah, you're sitting right next to him. Brett, did you hear that?
Yeah,
What did he say?
he said that couldn't you do the vertical line test on the inverse function?
Yeah. What the horizontal line test does for us is prevents us from having to find and graph the inverse. We can just look at the function and say, I'm not going to bother with it, it's not going to be a function, so who cares? That's pretty much, oh, hey, ooh, there's a fun word. Number one's pretty, yeah, if, yeah. No, you can all be excited about if. And I capitalize it. Yeah, capital if. Number 2, if f is strictly monotonic on its entire domain, then it is 1-to-1 and therefore an inverse function. Any idea?
Mono means one.
Probably touches it only one time on the graph.
Mono means one, tonic means, it's like seltzer water.
I'm thinking like tone for it. Am I close?
So, you say soap?
What did he say?
Soap? I said soap. So one seltzer
I
water?
thought you said soap.
I heard soap too.
You heard soap. Why would you say soap?
I said soap.
I heard soap.
We heard soap. You sure you didn't say soap and you think you said soap?
100% positive.
You're 100% positive that you think you said
200%
soap.
positive you said soap, dude.
I thought I heard it too. I wouldn't bet on it, but they're confirming that you said soap, which is fine. I mean, because you've already been nasty to Dante in the wrong direction, so I wouldn't be surprised if you just shouted out soap for no reason whatsoever other than to disrupt my lecture. Anyways, strictly monotonic. So you got the mono. Let's go back to the breakdown there.
So mono is one, tone. Tonic I'm thinking really back to tone, which means like waves or sound, I guess, how frequently.
It's not horrible.
Am I wrong now?
No. That's actually pretty close.
No.
How about strictly?
Not loosely.
So what does dog mean? Not cat. Weak sauce. Strictly monotonic means always increasing or always decreasing. So again, if you think of the wave, it's always going up or it's always coming down. And now you start thinking about geometry and or graphing again. In order to have it hit a horizontal line in more than one spot, it's got to go up and then come back down, or it's got to go down and then come back up. If it's always going up, you can't draw a horizontal line through there twice. And so we'll do a lot with that whole idea of always increasing or always decreasing. Over an interval. So we'll look at functions that might not be strictly monotonic, but they will be strictly monotonic on an interval. So if you look at x squared is not strictly monotonic, but it is strictly monotonic from 0 to infinity. You with me? Yeah. Good. Okay. Which of those has an inverse function? Now, I want you to answer the question thinking about calculus, not about algebra 1 or advanced algebra or graphing. Don't think about what the graph looks like. Think about it from a calculus standpoint. We can answer the question without calculating the inverse, because I don't really care what the inverse is. I just want to know if that inverse is a function. Any ideas? All right.
Wouldn't you have the inverse?
It wouldn't have an inverse because it's a parabola. I don't like pronouns. What won't have an inverse because what is a parabola? Be specific.
F of X won't have an inverse.
F of x won't have an inverse because
F prime is a parabola.
It's not strictly monotonic.
what's not strictly monotonic?
F prime.
Raj?
Doesn't f prime tell you that the slope is rising and then increasing and then, like it's decreasing and rising, so it's not monotonic.
Might be. How can we be sure?
It's the slope of the
If there's a negative, if f of x can equal a negative.
Not bad. There's a simple organization skill that you're forgetting about. Where are my critical numbers?
Oh.
Hold on, let's back up. How do we find a critical number?
Zero.
Take derivative set equals 0, solve. Okay, so if I solve that, what do I get for a critical number? Square root of negative 1/3. That's a problem in this class because we only do real numbers, so therefore, are there any critical numbers? No, so what do you know about this?
Strictly monotonic.
Because,
Doesn't change. Slopes.
what is it?
Always increasing.
Right, because this is positive. This can't be a negative value, so this is always increasing. Therefore, strictly monotonic. Therefore, the inverse is a function. Now we counter that with, of course, 2 examples. If one works, you can pretty much guess the other one's not going to work. Where are my critical numbers here? Close. Good. Plus or minus the square root of 1/3. I'm not even going to bother cleaning it up. I'm just going to throw it on there like this. Whoops. 1/3. Put in a very big positive number. I'll get a positive value. Increasing. Put in, what's a good number to put in here? 0. Negative. Uh-oh. Done. If that's all I needed to do, I'm not even going to test the last region because now I know what?
It's not strictly monotonic.
It's not strictly monotonic. Therefore,
It doesn't have an inverse.
no, it has an inverse,
It
but
doesn't have an inverse function.
good, it doesn't have an inverse function. Okay, so we got to be careful. Now, a couple things you should have gotten out of that interaction. Number 1, you have to be careful with the verbiage that you use. And number 2, eliminate pronouns from your discussion when we're talking about this. When you say things like it, I don't know what it is. Is it the function? Is it the derivative? You know what I mean? Get very specific. Okay. F of x inverse is not a function because the function is strictly back up here. F of x's inverse is not a function because it is not strictly monotonic. It's not strictly monotonic because, and this one, because the derivative changes from positive to negative, or the function is not always increasing or always decreasing. Okay, we good on that? I feel like I beat a dead horse here. Yes?
So you could have different critical numbers as long as they're all doing the same thing, it's still strictly monotonic.
Correct. Yeah, I could get something weird like that is possible. what you have to look at though is what happens at 1 and 4. You know, is it causing an issue? Is it a vertical asymptote? So it's possible, but doesn't necessarily have to be. I would not bet a lot of money that that's strictly monotonic because it has critical numbers there and you could have vertical asymptote. Okay. There's the graph, good, yep, yeah, we know that already. That one didn't work, doesn't pass horizontal line test, great. Okay, so then finding that inverse function, again, just to refresh what we already knew. Interchange the x and the y, solve for y, and what you're left with is that inverse function. Again, we're not going to do it a lot, but you should know how to do it. If I specifically ask you, here's a function, what's its inverse function, or what is the inverse, how to find it. Some basic algebra 2 stuff there. Notice back in 1, I've got HLT, which, well, what does HLT stand for?
Horizontal line test.
Horizontal line test or derivative. We did both. Horizontal line test, if you have the graph, just look at it, see if it passes the horizontal line test. If you don't have the graph, then you can go to the derivative, aka calculus method, to check whether or not that inverse is a function. Take the derivative, find the critical number, see if it's strictly monotonic. Test some points, blah, 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 blah. Okay, let's put this in motion here. We knew that already. The domain of the function is the range of the inverse. The range of, okay, here we go. Let's find the inverse of that guy. So that would be y equals the square root of 2x minus 3. Switch the x's and the y's. Ben, what do I do first?
Confirm that it is, that the inverse, that it has an inverse.
How?
Either using the horizontal line test or finding the derivative.
Okay. What does that graph look like? You want to do horizontal line test or you want to do derivative?
I'm really feeling the derivative here.
You want to go derivative?
Yeah.
Okay. Why are you shaking your head? You guys want to fight?
Be nice to people.
It doesn't mean you can't fight. I mean, it's just bring no emotion.
That's just sport.
So you can really model.
What's that look like?
Yeah.
Yeah, this. Whoa.
That.
How about like that?
That.
Is that strictly monotonic?
Yeah, that's,
Yeah.
Okay. Why?
It's always increasing.
It's always increasing, so strictly monotonic. It also passes the horizontal line test. If we wanted to do the derivative technique, though, we'd have to take the derivative of that function, which we can also do. It's just a little nasty. Well, it's not even that nasty. You just got it, whoops, squared. So f prime of x is equal to 1/2 times the quantity 2x minus 3 to the negative 1/2 times 2. That's going to cancel with that, and I'm left with 1 over the square root of 2x minus 3. Always positive, we're good to go. Okay. Now what, Ben? So I've confirmed that the inverse does have a function. How do I continue finding that inverse value, or function, I mean?
Switch the x and y.
Got it.
And then solve for y.
How?
Raise x, we'll raise both sides to the, raise both sides to the half. Wait. Square it, sorry.
I understand. I knew you'd get there eventually.
And then add 3 to the other side and divide by 2.
Plus 3.
Good. Thank you. Now we can go back and check that again by plugging f inverse into f and plug f into f inverse, but we don't need to because I know I did the math correctly to find that inverse. Okay, problems? Good, that's not even calculus stuff, so it's not that exciting. Let's get into some calculus. Okay, hey, there's a graph. Remember, a function and its inverse are reflections over the line y equals x. The point 2, 1 is on the graph, so therefore the point 1, 2 is on the graph. Yeah, we're going to need that in a second. Did that. Let's see. We verify it. Yeah, get x. We knew we'd get x. Got x down there. We're good to go. All right, derivative. Now I want to take an inverse function and take its derivative. And again, I'm going to show you two ways to do it. The first way is this big scary formula, which, go ahead, write it down. Just to make sure you understand the notation, what I'm saying here is I want the derivative of the inverse function. And in order to find the derivative of the inverse function, I'm going to take 1 over the inverse function plugged into the function and then taking the derivative. That's why I'm not a big fan of this method. I'll show you a different method in a second. So that means you need to find the inverse function. You need to plug it into the function itself, then take the derivative, do the reciprocal, you're good to go. But again, there's an easier way to do it. Got this? Okay, let's back up here. Come back here to, where's my picture? Come on. There we go. Okay, let's suppose this is my problem, and I want to find the derivative of the inverse at 1. Okay, so the problem would say, what is that? Okay, so what's a derivative? Derivative is 3 things. What are they? Slope of tangent line, good. Well, you combine 2 there. Instantaneous velocity and rate of change, good. Okay, well, which one do we care about here?
Slope.
Yeah, slope of the tangent line. I want to know
Clear it up here. Five we're doing up here.
guess we're not going to put an arrowhead on that one.
Oh, it's flat.
And it changed colors. How did that happen?
Magic.
Yeah, that's right. Yeah, Harry Potter smartboard. I want to know the slope of that line. You can use the formula, but there's an easier way, and one last trick I didn't explain. Can I find the slope of that line?
Yes.
Easy peasy, right? Take the derivative, plug in 2, I get the slope of that line. The question is, what's the relationship between the slope of those 2 lines? And it's an easy relationship. Okay. No. They look the same in this picture. That's not always going to be the case.
Is it that they're parallel?
No. Again, it just looks that way in the picture. It's not always going to be that way. If I go back to a further, wait, delete that. Are they what? I must have missed something because I heard them making fun of you. Did you say something wrong?
I said they're perpendicular.
They're not perpendicular. I can't even click back. I'm not even going to go back in. What do you
Could it
got?
just be 1 over the slope?
Good. It's a reciprocal slope. Okay. So not an opposite reciprocal like perpendicular, just a reciprocal slope. Reciprocal slope. Meaning, in order to find the answer to the question, I'm just clicking and there we go. In order to find the slope of the line that I had over here on the inverse function, I'm just simply going to find the slope of the line on the function itself, get an answer, and then just flip it over. Okay? Does that make sense? A couple things to remember. If I'm looking for the slope of the derivative at the inverse at 1, 2, I need to go back to the function to 2, 1. It's not the same point. Okay, so flip the A and the B. And then remember that the slope at the function is the reciprocal of the slope of the derivative, or I'm sorry, of the inverse. And hopefully that made some sense to you. So let's look at an example right here. I'm going to skip the first method, which is the formula, and just go right at it. here's the first problem. The point on the inverse where x is 3. So in other words, on the in the inverse, I have the point 3 comma something. Which means that I, yes?
You can finish your sentence.
Okay, which means that the point that I'm going to use to solve the problem is going to be something comma 3. Go ahead.
So then just plug in 3 for no, 3 for what? Set the equation equal to 3.
Good, set the equation equal to 3 and solve. Okay, do you understand why I'm doing that? What I'm looking for in the problem is what is the derivative of the inverse of f at 3? Which means I need to find the derivative on the original function at that other point. So I need to find this value for the inverse, which means I need to take 3 and set it equal to 1/4 x cubed plus x minus 1. I don't know about you, I don't know how to solve that. Do you? Now what do we do?
Cry.
Cry is one option, good. Not a bad idea, I'll come back to you in a second. We could go back to that monster, switch x's and y's and solve for y. That's going to be nasty too. Hey, how about we use some technology? Get out your calculators. Tell me what x is. So getting out your calculator is one thing. Knowing how to use the calculator to answer this question is an entirely different animal. How are you going to do this on a calculator? Be more specific. Graph what?
Graph that function set equal to 0, and then find the zeros, the x zeros.
Easier.
Plug in x for 3 on the graph and see what
No. Graph this, put this in y1, put this in y2, and see where they intersect. Because this will graph a horizontal line, right? We want to know where is y equal to 3, not x. So we want a horizontal line. And it's probably not going to be a pretty answer. I don't remember, to be honest.
2, 3.
It is a nice answer.
Very nice.
2?
Yeah.
Huh. I guess it is a nice answer. Awesome. That worked out better than I expected. Okay. Now, I happen to pick a cubic, which is not very easy to solve, so we have to use technology. If you don't have the technology, then the function would probably be easier. You probably get a quadratic where you solve it and find the values there. Okay, so now how do we proceed? Well, I know the point on the original function, so this is on f of x. If 3 comma 2 is on the inverse, then 2 comma 3 is on the function. Now I'm going to find f prime of 2, get a value, flip it over. Okay, so I need f prime of x. That's easy. 3/4 x squared plus 1. Find f prime of 2. That's 4, that's 3, that's 4. And so therefore, if I flip that over, I'll get this. And that should be my answer. I find that method a lot easier than just plugging and chugging into the formula, because the plugging and chugging in the formula can sometimes get a little nasty. And maybe because I teach so much geometry, I think of things in like a visual graphing sense. But if you understand the little snippets there, it will make this process fairly easy. Okay. Any part of that that you didn't get that you want me to review, like where any of those numbers came from? Yeah.
Can you repeat the last part on why the prime of x to the, yeah, what's that?
I know that the point 3,2 is on the inverse, and I want to find the derivative at that point on the inverse.
Okay,
Its corresponding point on the function itself is 2, 3.
yeah.
So if I can find the slope of the tangent line at 2, 3 on the original function, then take the reciprocal, I got my answer. because the relationship between the slope of the line on the derivative and the slope of the line on the inverse, I'm sorry, on the function and the inverse are reciprocals of each other.
So, yeah, so you took the derivative of the f of x at the time.
Correct.
Okay.
Yes. It allows me to not have to find what the inverse is, and I can just go from there. Maggie?
Can you go one more time why you set 3 equals to 1/4 of x cubed?
Okay, so I know that I'm looking for this.
Right.
So on the inverse function, what's the slope of the tangent line at 3?
1/4.
Okay. Right. But in order to get there, I need to know its corresponding point on the original function,
Okay.
which means I have the, if 3 is the x value, then 3 would be the y value on the original function.
Okay.
And I need to find the x value.
Uh,
So I plug that 3 in for the original function, because I don't know what the inverse is, nor do I care. Solve that, and again, I had to use a calculator to do that because I didn't know what it was, and I got the point.
Okay.
Okay? No. Sometimes those functions will be something easy, like a quadratic or a linear term where you just set it equal, and so, you know, so if my function was like 2x minus 1, set that equal to 3 and solve, you get it.
Mr. Reed,
Yeah,
what's the answer in the top circle? I can't read it.
1/4,
And then where'd you get that?
the reciprocal of 4.
Oh.
Anything else before I erase? Yeah, this is all we did. Okay, so yeah, yeah, okay. Done. Okay, so that's the other method that I described, opposite reciprocal. Not the opposite reciprocal. And I don't think we need to do that. That's just confirming what I already told you. If you go through the problem here, you'll figure out that it confirms what I said, that they are reciprocals of each other, which allows you to solve all that. So we'll skip all that, and I think we're done. Good. Okay? 5-3. One day on this, it's not incredibly important. The most important part out of this is understanding the terminology and being able to find the derivative of the inverse at a certain point.
With the graphing, could you have subtracted the 3 over and found the zeros?
Yes, that would be another way to do it.